Hello there, students. In this video, we're going to take a look at a few examples of common vector type problems you might encounter in textbooks. For each problem, it'd be good to try it on your own first to see if you understood the material from the previous videos, but I'll go over each answer too. For the first question, suppose you're asked to find vector d, given this equation for it and the following vectors. Pause the video, see if you can get the answer. Welcome back. So I started by plugging in every vector, and then computed the dot product between vectors a and c, which is in the parentheses. Then, I multiplied all the scalars together outside the second vector, and multiplied the scalar through the first vector. Remember, those scalars act on every vector component. Multiply that scalar through the second vector, and then add the vectors together component by component. For the second problem, if you walk 2 kilometers east and then 5 kilometers north, how far are you from where you started? And what angle does this position vector make with the east axis? Pause the video and try this one out. Welcome back. When you're asked how far you are from something, this usually means you need to find a vector's magnitude. I would first draw a diagram, something like this, where the x-axis is east and the y-axis is north. We're given the components of vector A in the problem, so we can find its magnitude no problem. For the next part of the question, we're asked to find the angle that this vector A makes with respect to the east axis. In my diagram, that is the x-axis, and the angle in question is labeled as theta. We can use the trigonometric definition of the tangent of theta, then take the inverse tangent to isolate the angle theta. Plugging this into a calculator, we get our result. On to problem 3. Here, we're asked to calculate vector c, given an equation for it and the following vectors. Pause the video, give this one a shot. Welcome back. To start, I'll calculate the first cross product here. If you had trouble here, give my cross products video another try. Now, I could have calculated the other cross product next, vector b cross a, but as many of you probably figured out, there's a nice identity we could use here instead. It turns out that if you switch the order of the vectors in a cross product, all you do is pick up a negative sign. If you're unsure of this, I encourage you to try and prove it yourself. It's not too difficult, I promise. Since the second cross product in our equation is just reordering our original cross product, we can just substitute in the cross product we've already solved. The 3 dots here is just math shorthand for therefore. Making that substitution, we see vector c is actually just 2 times the first cross product. Multiplying that scalar through the vector, we get our final result for vector c. For our fourth problem, I want you to take a look at each of these and determine which of the following are valid expressions. Pause the video and think about these. Welcome back. So here are the valid and invalid expressions. Letter A is not valid because we're trying to add a scalar, the number 3, to a vector which is not allowed. Letter B is not valid because if you look closely at the last part of the expression, we have in parentheses a dot product between vector b and c, which itself is valid, but that scalar result is then going to be in a cross product with vector b, and we can't cross a vector with a scalar like that. Letter C is completely valid. We have a dot product producing a scalar, and then multiplied by a unit vector. Then we're adding the result of a cross product which is another vector. All good here. Letter D is also valid. In the parentheses, we have a cross product which makes a new vector from which we subtract off vector c. This means the final result in the parentheses is a vector, which we then dot with vector b, returning a scalar. For our fifth and last problem, we're getting a little more difficult. Given 2 vectors, d1 and d2, what is the result of these operations? Pause the video, take a quick ponder. Welcome back. We could compute each product and get the result, but I think it's more interesting to solve this problem geometrically. Let's first consider two arbitrary points in three-dimensional space. We can connect these 2 points with a line, meaning any 2 points have in common some shared line. This idea also holds for any 2 vectors, in that any 2 vectors can be connected by a shared 2-dimensional plane instead of a 1-dimensional line. What this means is that vectors d1 and d2 are coplanar. They both lie on some shared plane. So, when we add them together in the first set of parentheses, that new vector is also on that same shared plane. Much like when we are working in 2-dimensional Cartesian space, or x and y coordinates, each vector only has an x and y component. If we add any arbitrary vectors together in these 2 dimensions, they're always still on the same plane as we started, the x and y coordinate space. In the second set of parentheses, we have the same 2 vectors, vector d1 and d2, but now we have a cross product between them. A cross product always produces a vector that is perpendicular to both of the original vectors, meaning whatever vector is produced from this cross product, it is perpendicular to the entire plane that vector d1 and d2 share. And for that matter, it's perpendicular to the new vector made by adding together vectors d1 and d2, because that too is on that same plane with vectors d1 and d2. The last step is that dot product. We have a dot product between a vector on the shared plane with d1 and d2, and a new vector, which by definition must be perpendicular to that plane. This dot product will always be 0. It will cast no shadow. If this was a lot to grapple with, I encourage you to actually compute these to see the result for yourself. Thanks for watching and learning about vectors. If you found this series helpful or want to see a specific topic covered, post a comment below or head over to my Facebook page.